settle in. Whatever room you're in, whatever bed you have found, this place will hold you for the next while. Loosen your shoulders, let your jaw soften. Tonight, with no hurry at all, we are going to drift very slowly into the deep, slow story of the rarest stars in the universe, where neutron stars spin in silence, magnetars hum with fields beyond imagining, and hypergiants quietly outweigh hundreds of suns across the patient cosmic dark. This is the Circadian Institute. We make slow, scientifically grounded stories meant for sleep. The voice is steady, the pace is patient. Tonight's destination is the deep, slow story of the rarest stars, the tiny, dense neutron stars that pulse like cosmic clocks, the magnetars with the most powerful magnetic fields in the known cosmos, the Wolf-Rayet stars wrapped in expanding shells of their own gentle outflow, the hypergiants that fill volumes larger than entire planetary orbits, the white dwarfs slowly cooling toward an eternal cosmic rest, and all the strange and beautiful stellar lives that only a few sky surveys ever encounter. Subscribing is the small gesture that keeps these journeys reaching new sleepers each night. Tonight, we will travel together through some of the most unusual stars in the universe. We will visit the dense, quiet neutron stars, the magnetars with their mysterious fields, the hypergiants larger than entire solar systems, the brown dwarfs that almost became stars, the cooling white dwarfs that slowly fade into cosmic night, and many other strange and gentle stellar phenomena. There is no hurry. We have all the time we need. To begin tonight's journey, we will visit the smallest known stars in the cosmos. They are called neutron stars. Each one is the collapsed remnant left behind after a massive star ends its life. Each one is no larger than a quiet city, perhaps 20 kilometers across. Yet inside, packed into that small cosmic volume, sits more matter than the sun itself. To imagine a neutron star, you can begin with our sun. The sun is roughly 1.5 million kilometers across, and it holds the mass of about 1 million Earths. A neutron star is even more concentrated. Take that sun, take all of its mass, and squeeze it into a sphere only 20 kilometers wide. The result is a neutron star. The density inside a neutron star is unlike anything else in the known universe. A single teaspoon of neutron star material would weigh roughly 6 billion tons here on the planet, more than the mass of every human ever born. The matter inside is not made of ordinary atoms. It is made almost entirely of neutrons, packed shoulder to shoulder, forming a quiet sea of tightly bound particles. Neutron stars form when a star much heavier than our sun reaches the end of its long life. After billions of years of slow nuclear fusion, the star's core runs out of fuel. The outer layers collapse inward in a final cosmic event. Most of the energy escapes as a brilliant supernova, lighting up the surrounding space. What remains in the very center is the dense, quiet neutron star. The first neutron star ever detected was found by accident. In 1967, a young astronomer named Jocelyn Bell was studying radio signals at Cambridge. She noticed a strange, faint signal that pulsed exactly every 1.3 seconds, far too regular to be natural. The signal was nicknamed LGM-1, short for Little Green Men, before astronomers realized they had discovered the first known pulsar. That first pulsar is now called PSR B19 plus 21. It is a neutron star roughly 2,000 light-years away from Earth, spinning so smoothly that its pulses arrive on a precise cosmic schedule. Tonight it is still rotating, still releasing its faint radio beam in our direction every 1.3 seconds, exactly as it has for far longer than human history. Most neutron stars rotate quickly because their parent stars also rotated, and when the core collapsed, the rotation became concentrated into a much smaller space. The same physics is at work when a figure skater pulls in their arms during a spin. Some neutron stars rotate once every few seconds, others rotate hundreds of times per second. The fastest spinning neutron star ever observed is named PSR-J 1748-2446 AD. It rotates 716 times every second. The surface of that neutron star is moving at nearly a quarter of the speed of light. Despite this enormous rotation, the neutron star itself remains extraordinarily smooth and stable, only quivering by fractions of a millimeter in any given moment. Neutron stars also possess the strongest magnetic fields of any ordinary stellar body. A typical neutron star has a magnetic field roughly 1 trillion times stronger than the magnetic field at Earth's surface. The magnetic field shapes how the star releases energy, channeling charged particles outward along the magnetic poles in narrow cosmic beams. The surface of a neutron star is thought to be made of a thin crust of crystalline iron-rich material, perhaps only a few hundred meters thick. Beneath the crust lies a vast inner ocean of neutron-rich superfluid, a strange phase of matter that flows without any internal friction at all. Below that, in the deepest interior, the matter may transition into something even more exotic, perhaps free quarks, no longer bound into ordinary neutrons. Astronomers have detected several thousand neutron stars in our galaxy alone, but the total number must be far higher. Most neutron stars are not pulsars and do not send detectable radiation our way. The total number in the Milky Way is thought to be around 1 billion, though only a small fraction will ever be discovered. Each one is a quiet cosmic remnant of an ancient massive star. The temperature on the surface of a young neutron star can exceed 1 million degrees Celsius. Slowly, over millions of years, neutron stars cool by emitting faint X-ray radiation into deep space. After 10 million years, a neutron star may have cooled to a surface temperature of 100,000 degrees. After 1 billion years, it may have cooled even further. The very oldest neutron stars in our galaxy are now nearly invisible. One of the most famous neutron stars in the night sky is the Crab Pulsar. It sits at the center of the Crab Nebula, a beautiful cloud of cosmic gas and dust about 6,500 light-years from Earth. The Crab Pulsar spins 30 times every second. Astronomers can see it pulse in radio, in visible light, in X-rays, and in gamma rays, making it one of the most thoroughly observed objects in the cosmos. The Crab Pulsar formed in a supernova that human astronomers actually observed in the year 1054. Chinese and Arab astronomers recorded a brilliant new star in the night sky, visible even during daylight for nearly a month. Tonight, what they saw is now the soft, expanding nebula of the Crab, with the dense neutron star spinning quietly at its heart. releasing its rotational energy into the surrounding space. Neutron stars sometimes experience small abrupt changes in their rotation, called glitches. The star is spinning normally, then suddenly speeds up by a tiny amount, then continues smoothly again. Astronomers believe glitches happen when the inner superfluid of the neutron star transfers some of its rotational energy to the outer crust. The whole event takes place in a fraction of a second. Some neutron stars are not alone. They orbit a companion star, sometimes very closely. In these binary systems, matter from the companion can flow onto the neutron star, releasing energy as X-rays. These accreting neutron stars are some of the brightest X-ray sources in the entire sky. They have helped astronomers measure the masses, sizes, and inner structures of neutron stars with extraordinary precision. In 1992, astronomers used a neutron star to make a remarkable discovery. By measuring tiny variations in the timing of pulses from the pulsar PSR B1257+12, they detected the gravitational influence of 3 orbiting bodies. These were the very first planets ever discovered outside our solar system. They orbit a dead neutron star, far from any sunlight, in the long, quiet aftermath of a supernova. Tonight, neutron stars continue their long, patient existence across the cosmos. They spin in silence. They cool slowly. They release faint, cosmic pulses across the deep dark of space. They are among the most extreme objects in the universe, and yet in their own way they are also among the calmest, simply being what they are across spans of cosmic time far longer than any human story. From the broader family of neutron stars, we now turn to the special subset called pulsars. A pulsar is simply a neutron star whose magnetic poles happen to point toward our planet at some moment in its rotation. Each time the magnetic axis sweeps past Earth, we receive a brief pulse of radiation. The neutron star itself is shining steadily into space, but we only see the beam when it points our way. This geometry is similar to a cosmic lighthouse. A lighthouse spins continuously its lamp, pointing in one fixed direction relative to the spinning structure. As the structure rotates, the beam sweeps across the surrounding sea. Sailors only see the lighthouse during the brief moments when the beam crosses their horizon. A pulsar works in essentially the same way, only across spans of cosmic distance. The pulses from a pulsar arrive with extraordinary regularity. Some pulsars are so reliable that they rival the best atomic clocks ever built by human hands. PSR B1937+21, for example, pulses 642 times per second with timing accuracy better than 1 part in a quintillion. It is one of the most stable timekeepers in the known cosmos. After the discovery of the first pulsar in 1967, astronomers quickly found many more. Within a few years, dozens of pulsars had been catalogued. Today, the total count exceeds 3,500. Most of them lie within our own Milky Way galaxy, though a handful have been detected in nearby galaxies as well. Pulsars come in different categories based on their rotation periods. The slowest known pulsars rotate once every several seconds. Standard pulsars spin in the range of half a second to a few seconds. Fast pulsars spin many times per second. The fastest are called millisecond pulsars, completing hundreds of rotations every second. The Vela pulsar is one of the most famous in the southern sky. It sits within the Vela supernova remnant, about 1,000 light-years away. Vela rotates roughly 11 times per second. Its magnetic pulses can be seen across many wavelengths, from radio to X-rays to gamma rays. Vela is one of the strongest pulsars seen in gamma-ray light from anywhere in the cosmos. Millisecond pulsars rotate so rapidly that they would once have seemed impossible. The fastest examples spin near the theoretical limit, where any faster rotation would tear the star apart. Most millisecond pulsars formed in binary systems. A nearby companion star transferred matter onto the neutron star over millions of years, slowly accelerating its spin to extreme rates. Astronomers call these spun-up neutron stars recycled pulsars. They were once ordinary, slow-rotating remnants. Then, over a long, quiet stretch of cosmic time, the gentle infall of matter from a companion star gradually accelerated their spin. By the end of this slow recycling process, they emerged as some of the fastest spinning objects known. Among pulsars, glitches are one of the most fascinating phenomena. A pulsar is rotating smoothly, its pulses arriving on schedule. Then, in a sudden moment, the pulsar speeds up by a tiny fraction. Astronomers believe this happens when the superfluid neutron interior transfers a small amount of rotational momentum to the solid outer crust. The pulsar then continues at its new, slightly faster rate. Some pulsars also show drifting subpulses. Within each main pulse, there are smaller substructures that drift slowly across the pulse profile. The pattern repeats from one rotation to the next. These subpulses are not yet fully understood. They appear to involve plasma physics happening near the pulsar's magnetic poles, where charged particles are accelerated into the cosmic beam. There is also a rare subset called rotating radio transients, or RRATS. These objects emit only occasional pulses, sometimes minutes or hours apart. Most of the time they are silent. Then briefly a pulse appears and the underlying neutron star reveals itself. RRATS are difficult to detect, and many more must exist than have been found so far. In 1992, the pulsar PSR B1257+12 was found to host the very first known exoplanets. The astronomers Alexander Wolszczyn and Dale Frail measured tiny periodic variations in the pulsar's pulse arrival times. Those variations were caused by the gravitational pull of small planets orbiting the dead star. It was a remarkable discovery, made possible by the precise cosmic timing of pulsars. Pulsar timing has also become one of the most powerful tools for detecting gravitational waves. By monitoring many pulsars across the sky and looking for tiny correlated variations in their pulse arrival times, astronomers can search for the gentle ripples of spacetime caused by distant supermassive black hole mergers. This effort is called a pulsar timing array, and it represents some of the most precise astronomy ever attempted. Pulsars do not last forever. As they rotate, they lose a small amount of rotational energy through the magnetic beams they produce. Over millions of years, this slow drain causes them to spin down. Eventually, the rotation becomes too slow for the magnetic field to produce visible beams. The pulsar enters a quiet phase. the radio emission fades. The neutron star continues to exist, but it is no longer detectable as a pulsar. The relationship between a pulsar's rotation period and its rate of spin down is so reliable that astronomers can estimate a pulsar's age from these two quantities alone. Young pulsars spin quickly and slow down quickly. Old pulsars spin slowly and slow down very slowly. The Crab pulsar, for example, is thought to be about 1,000 years old. Some of the oldest known pulsars are tens of millions of years old. A few pulsars are found in particularly extreme environments. Some pulsars are part of dense globular clusters, where many stars sit very close together in these crowded cosmic neighborhoods. Pulsars sometimes interact with other stars over long stretches of time. Some have multiple companions in their history. Some have been ejected and recaptured. Tonight, pulsars continue their cosmic timekeeping across the universe. Some pulse thousands of times per second. Some pulse only every few seconds. All of them release their tiny, faint cosmic beams into the dark on schedules that have been kept far longer than human history. They are among the most reliable phenomena in the universe. Now, gently, we will move from the regular pulsing of ordinary pulsars to a much rarer and more extreme cosmic phenomenon, the magnetars with their fields beyond imagining. Among the rare neutron stars in the universe, magnetars are the most extreme. A magnetar is a neutron star with a magnetic field roughly 1,000 times stronger than that of an ordinary pulsar. The magnetic field strength of a magnetar can reach 10 to the 15th Gauss, a number so large that ordinary matter, if it were anywhere nearby, would be quietly distorted by the field alone. The first magnetars were proposed theoretically in the 1990s, before any observations could confirm them. The astronomers Robert Duncan and Christopher Thompson developed the theory based on the strange behavior of certain pulsing X-ray sources in the sky. They suggested that some neutron stars carry magnetic fields far beyond anything previously imagined. Subsequent observations confirmed their idea. Today, astronomers know of about 30 confirmed magnetars in our galaxy. The total number must be far higher, but most magnetars are quiet most of the time. They become detectable mainly when they release energy in sudden bursts, after which they fade back into apparent stillness. A magnetar's magnetic field is so strong that the field itself dominates the physics of the surrounding region. Light rays passing close to the surface are bent gently by the magnetic field. Atoms in the immediate environment cannot exist in their familiar shapes. The vacuum itself becomes slightly birefringent, meaning that light passes through it differently depending on its polarization. The magnetic field of a magnetar exerts enormous stress on the star's solid crust. As the field slowly evolves, it twists and rearranges itself. Sometimes this stress builds up until the crust suddenly shifts. The shift is called a starquake, and it can release vast amounts of energy in a fraction of a second. On December 27th in the year 2004, a giant flare from the magnetar SGR 1806-20 arrived at Earth. The burst was so bright in gamma rays that it briefly outshone every other source in the sky combined. The magnetar was about 50,000 light-years away in the constellation Sagittarius. The flare lasted about a fifth of a second. That single brief flare released more energy than the Sun has produced in its entire lifetime. It briefly disturbed the outer atmosphere of Earth, shifting electrical layers 50,000 light-years away. It is one of the most energetic events ever recorded in our galaxy, and yet the magnetar that produced it has been quiet ever since. Astronomers classify magnetars into two observational types. Soft gamma repeaters release sporadic short bursts of soft gamma rays. Anomalous X-ray pulsars release steady or slowly varying X-ray emission. The two categories are now understood to be different observational expressions of the same underlying object, a neutron star, with an extremely strong magnetic field. The magnetar 1E1048.1-5937, located about 9,000 light-years away, has been observed for many years. It rotates once every 6.5 seconds. It releases X-rays steadily into space. Occasionally it produces small soft gamma bursts. It is one of the most thoroughly studied magnetars in our galaxy. In recent years, magnetars have been linked to one of the most surprising cosmic phenomena, fast radio bursts. These are extremely brief but powerful flashes of radio waves arriving from distant galaxies. Most fast radio bursts are too far away to be associated with any specific source. But in April of 2020, the magnetar SGR 1935+2154 in our own galaxy produced a fast radio burst that astronomers could trace. That observation strongly suggested that magnetars are responsible for at least some of the fast radio bursts seen across the universe. The exact mechanism is still being explored. The leading idea involves sudden reconnection events in the magnetar's powerful magnetic field, which release brief bursts of coherent radio emission outward into space. Magnetars are rare partly because their extreme magnetic fields decay over time. The field loses energy through ohmic heating, gradual dissipation, and the small bursts that the magnetar occasionally releases. Within roughly 10,000 years, the magnetic field weakens enough that the magnetar becomes a more ordinary neutron star. The active magnetar phase is brief in cosmic terms. Despite their rarity in the present, magnetars have probably been important throughout the history of the cosmos. Every time a sufficiently massive star ends its life and collapses into a neutron star, there is a small chance that the resulting object will become a magnetar. Many magnetars have come and gone across the long history of the universe. Some theories propose that magnetars may also play a role in producing certain types of cosmic gamma-ray bursts. Long gamma-ray bursts are usually associated with the deaths of very massive stars. Short gamma-ray bursts come from neutron star mergers, but intermediate duration bursts may sometimes come from magnetar flares scaled up to truly enormous proportions. The crust of a magnetar is thought to be only about a kilometer thick, sitting on top of a neutron-rich superfluid interior. The crust is not perfectly smooth. It has tiny ridges, perhaps only a few millimeters high, held in place by the enormous magnetic stress and the tremendous gravitational pull of the underlying neutron star. If you could approach a magnetar, though no spacecraft will ever do so, you would notice the magnetic field long before you arrived. At 1,000 kilometers from the surface, the magnetic field would be powerful enough to disrupt every atom in the approaching probe. At 100 kilometers, the field strength would exceed every magnet ever made on Earth combined. The magnetar would dominate everything. Tonight, The small population of magnetars in our galaxy continues quietly. Most of them are silent right now, their magnetic fields slowly evolving in the dark. A few may be releasing small, unnoticed bursts across the rest of the cosmos. The same pattern is repeating in countless other galaxies. The total population of magnetars throughout the observable universe must be enormous, even though only a few are ever actively observed. Now gently, we will leave the small, dense magnetars behind and move toward stars at the opposite extreme of size, the enormous Wolf-Rayet stars with their slow expanding cosmic shell. Wolf-Rayet stars are among the brightest and most short-lived stars in the universe. Each one has a mass of at least 20 times that of the Sun, sometimes much more. Each one is in the late stages of its stellar life, and each one is releasing matter into space at extraordinary rates, slowly stripping away its own outer layers across spans of cosmic time. These stars take their name from the two French astronomers, Charles Wolf and Georges Rayet, who first observed their unusual spectra in 1867. They noticed strange bright emission lines in the light from three particular stars in the constellation Cygnus. Most stars show absorption lines. These three showed strong emission. Something unusual was happening in their atmospheres. Today, astronomers understand that Wolf-Rayet stars have lost most or all of their original outer hydrogen envelopes. What remains exposed at the surface is hot inner material, primarily helium, sometimes carbon, sometimes oxygen and nitrogen, depending on which evolutionary stage the star has reached. The bright emission lines come from the dense, hot stellar wind streaming outwards. The stellar winds of Wolf-Rayet stars are remarkable. A typical Wolf-Rayet star is losing matter at a rate roughly 1 million times higher than the present rate of mass loss from the Sun. The wind is moving outward at speeds of 1 to 3,000 kilometers per second. Across a few 100,000 years, an entire stellar mass can be released into the surrounding cosmic environment. Wolf-Rayet stars are typically classified into three main spectral subtypes. The WN stars show strong nitrogen emission and are still showing the products of the carbon-nitrogen-oxygen fusion cycle. The WC stars show strong carbon and oxygen emission, indicating an even later stage of stellar evolution. The very rare WO stars show even more advanced products, including strong oxygen emission and very thin remaining outer layers. One of the most famous Wolf-Rayet stars is WR124, located about 15,000 light-years from Earth in the constellation Sagitta. The James Webb Space Telescope captured a spectacular image of this star surrounded by an enormous nebula of gentle cosmic dust. The dust shells extend many light-years outward and contain about 10 times the mass of the Sun's worth of expelled stellar material. The dust around WR124 was probably produced over the past tens of thousands of years. As the hot stellar wind moves outward and slowly cools, gas atoms gradually condense into solid grains of cosmic dust. These grains then continue to drift outward into the surrounding interstellar medium, eventually mixing with the broader galactic environment. Wolf-Rayet stars are some of the hottest stars in the universe. The surface temperature of a typical Wolf-Rayet star is between 30,000 and 200,000 Kelvin. By comparison, the Sun's surface temperature is about 5,700 Kelvin. The most extreme Wolf-Rayet stars emit most of their radiation in the ultraviolet, far beyond what human eyes could see directly. Wolf-Rayet stars are also extremely luminous. The brightest examples can shine with 1,000,000 times the luminosity of the Sun. Despite their relative scarcity, they contribute a noticeable fraction of the total ultraviolet light produced in their host galaxies. The radiation from a Wolf-Rayet star can dominate its immediate cosmic neighborhood for many light years around. Despite their brilliance, Wolf-Rayet stars are very short-lived. Each one typically remains in the Wolf-Rayet phase for only a few 100,000 years. After this brief stellar epoch, the star's evolution comes to its end. The exposed hot core can no longer support fusion. The remaining outer material is largely gone. What follows depends on the star's mass and detailed properties. Most Wolf-Rayet stars are believed to end their lives as supernovae. Some leave behind black holes, others leave behind unusually massive neutron stars. A few may collapse directly into black holes without producing a visible supernova at all. The Wolf-Rayet phase represents the very late stages of the most massive stellar lives. Some Wolf-Rayet stars exist in binary systems where their stellar wind interacts with the wind of a companion star. This can produce dramatic colliding wind effects, where the two outflows meet at high speeds and produce strong X-ray emission and beautiful spiral patterns of cosmic dust. The famous binary WR104 shows exactly this pattern, producing a delicate cosmic spiral that has been imaged in extraordinary detail. Wolf-Rayet stars contribute significantly to the chemical evolution of galaxies. The matter they release into space contains heavy elements forged in the deep interiors of massive stars. As this material drifts outward, mixes with the surrounding interstellar gas, and eventually finds its way into new generations of stars and planets, it carries the elemental signature of its Wolf-Rayet origin. In the broader picture, Wolf-Rayet stars are connected to long gamma-ray bursts, some of the most energetic events known in the entire cosmos. When a particularly massive Wolf-Rayet star collapses, the resulting hypernova may produce a powerful pair of gamma-ray jets that travel across the universe. Some of the gamma-ray bursts detected by satellites every year may originate from the deaths of distant Wolf-Rayet stars. Astronomers have identified roughly 500 Wolf-Rayet stars in our own galaxy. The total population must be slightly higher, but Wolf-Rayet stars are intrinsically rare because they represent a brief late phase in the life of a very massive star. Massive stars are themselves uncommon, and the Wolf-Rayet phase only lasts for a small fraction of even those rare stellar lives. Some galaxies are particularly rich in Wolf-Rayet stars. The Large Magellanic Cloud, a small companion galaxy to our Milky Way, contains several hundred known Wolf-Rayet stars. The nearby starburst galaxy NGC 313-400 contains many more. These Wolf-Rayet-rich environments tend to be regions of recent and intense star formation. Tonight, Wolf-Rayet stars across the universe continue their slow, patient release of matter into surrounding cosmic space. The dust they produce will eventually become part of new molecular clouds. The new clouds will eventually contract under gravity. New stars and planets will eventually form. The chemical composition of those future stars will be subtly enriched by the Wolf-Rayet contributions of the past. Now gently, we will leave the brilliant Wolf-Rayet stars and travel toward stars even larger and more massive, the Hypergiants, the largest known stars in the universe. The Hypergiants are the largest stars known to exist in the universe. Each one is so vast that it would dwarf entire planetary systems. Each one is so luminous that it could be seen across many thousands of light years of cosmic distance. And each one is so brief in cosmic terms that the entire stellar life lasts only a few million years before reaching its quiet end. To imagine the size of a hypergiant, consider the largest known stars compared to our Sun. The Sun has a diameter of about 1 4/10 kilometers. Some of the largest hypergiants have diameters more than 1,500 times larger than the Sun. If such a hypergiant replaced the Sun in our solar system, its surface would extend beyond the orbit of the planet Jupiter. VY Canis Majoris is one of the most famous hypergiants. It lies about 3,800 light-years from Earth in the constellation Canis Major. Its diameter is roughly 2,000 times that of the Sun. If it were placed at the center of our solar system, its surface would extend beyond the orbit of Saturn. It is a slowly evolving cool red hypergiant, releasing material into space across long cosmic timescales. UY Scuti is another famous hypergiant. It lies about 9,500 light-years from Earth in the constellation Scutum. Its diameter is estimated at roughly 1,700 times the diameter of the Sun. Its outer atmosphere is so diffuse that the star is hardly more than a slow, gentle expansion of stellar material into surrounding space. It is one of the largest known stars by volume. Stephenson 2-18 is a hypergiant in the open cluster Stephenson 2, about 20,000 light-years from Earth. Recent estimates suggest its diameter could be more than 2,000 times that of the Sun, possibly the largest of any known star. The estimate is uncertain because the star sits within a complex region of the galaxy that makes precise measurements difficult. 136. A1 is a different kind of hypergiant. While many hypergiants are red and cool, our 136A1 is a hot blue Wolf-Rayet hypergiant. It lies about 160,000 light-years from Earth in the Tarantula Nebula of the Large Magellanic Cloud. Its mass is estimated at roughly 215 times the mass of the Sun. It is one of the most massive stars ever observed. Mu Cephei is a relatively close hypergiant about 2,400 light-years from Earth in the constellation Cepheus. Its diameter is roughly 1,400 times that of the Sun. It is also called the Garnet Star because of its distinctive deep red color when seen through a telescope. Tonight, it remains visible in the northern sky. KY Cygni is another red hypergiant in the Cygnus region, located about 5,000 light-years from Earth. Its size is estimated at roughly 1,200 times that of the Sun, though estimates of these very large stars often carry significant uncertainty. KY Cygni shines with the light of about 1 million suns at the same time. Hypergiants are surrounded by extremely diffuse atmospheres. The boundary between the star and surrounding cosmic space is not sharp. Instead, the outer layers gradually fade into the surrounding interstellar medium with no clear edge. This makes precise measurements of size and luminosity unusually difficult, and different methods sometimes give different answers. Hypergiants lose mass at extraordinary rates. The strongest examples can lose the equivalent of 1 Earth mass per year through stellar wind alone. Sometimes, larger eruptions release enormous amounts of material in shorter intervals. Over the course of a hypergiant's brief stellar life, the total amount of material released can equal a significant fraction of the original stellar mass. Many hypergiants show variable luminosity over time. Their brightness rises and falls on timescales of months to years, with no perfectly regular cycle. The variability is caused by complex interactions between the star's enormous radius, its convective envelope, its slow pulsations, and its changing rate of mass loss. Even tonight, many distant hypergiants are quietly fluctuating in brightness. Some hypergiants have produced significant cosmic events in their history. Eta Carinae, a hypergiant in the constellation Carinae, underwent a brief brightening event in the 1840s known as the Great Eruption. During that event, Eta Carinae briefly became the second brightest star in the southern sky. We will visit Eta Carinae more closely in a later chapter tonight. The interior structure of a hypergiant is unusual. The very center hosts intense nuclear fusion, producing iron and other heavy elements. The surrounding layers contain shells of different fusion processes, each one a few thousand kilometers thick. The outer envelope is a vast convective region of relatively cool, highly ionized material. The whole interior is constantly mixing and adjusting in slow but ceaseless cosmic motion. Hypergiants are believed to evolve from very massive main sequence stars, typically those starting out with 30 or more times the mass of the Sun. As the original star ages, its core nuclear fusion changes through a series of stages, each producing heavier elements. Throughout this evolution, the outer layers expand to enormous radii, and the star eventually arrives at the hypergiant phase. Eventually, every hypergiant reaches the end of its evolution. The final fate depends on the precise mass and composition of the star. Some hypergiants are believed to end as ordinary core collapse supernovae. Others may produce hypernovae, particularly energetic stellar deaths that can leave behind black holes. A few may even collapse directly to black holes without any visible supernova at all. Despite their enormous size and luminosity, hypergiants are very rare. Within our entire Milky Way galaxy, only a few dozen confirmed hypergiants are known. The total population must be slightly higher since hypergiants spend a relatively brief time in the most luminous phase, but compared to ordinary stars, hypergiants represent perhaps 1 in a million. Tonight, hypergiants across the cosmos continue their slow stellar lives. Some are slowly losing mass into surrounding space. Some are gently pulsating in their outer atmospheres. Some are approaching the final phase of their existence. All are doing what hypergiants do, being patient, being enormous, being among the most spectacular stars in the universe. Now we will move from the hypergiants to a related but distinct family, the red supergiants. These stars are smaller than hypergiants but still enormous, and several of them are bright enough to see with the unaided eye on a clear night. Red supergiants are the cool, expanded final phase of many massive stars. Each one is far larger than the Sun, sometimes 1,000 times wider. Each one shines with the light of tens or hundreds of thousands of suns combined, and several of them are visible to the unaided eye in the night sky, slowly drifting through their last few 100,000 years of stellar life. Betelgeuse is the most famous red supergiant of all. It marks the right shoulder of the constellation Orion, easily visible in the winter sky. Betelgeuse lies about 500 light-years from Earth. Its diameter is roughly 700 times that of the Sun. If Betelgeuse were placed at the center of our solar system, its surface would extend somewhere between the orbits of Mars and Jupiter. Betelgeuse is one of the few stars whose surface has actually been imaged from Earth. The Hubble Space Telescope, The Very Large Telescope and other instruments have produced detailed images showing not just a point of light, but a small disk with brightness variations across its surface. These variations correspond to enormous convective cells, some of them larger than the entire orbit of Earth around the Sun. The convective cells on Betelgeuse are vastly larger than anything that exists on the Sun. Solar convective cells are about 1,000 kilometers across. Betelgeuse convective cells can be hundreds of millions of kilometers across. They rise from the deep interior, transport heat to the surface, then sink back down on slow timescales of years to decades in patient cosmic motion. In late 2019 and early 2020, Betelgeuse experienced an unusual dimming event. Its visible brightness dropped to about 1/3 of its normal level. For a few months, the star looked noticeably fainter in the night sky. Some speculated that Betelgeuse might be approaching its final supernova. The actual cause was much more peaceful. A large cloud of cosmic dust had condensed in front of the star, partially blocking its light. After several months, the dust dispersed. Betelgeuse returned to its normal brightness. The event was a beautiful reminder of how much remains unknown about even the closest red supergiants. Slow processes in their atmospheres can produce visible changes that are hard to predict in advance. Antares is another famous red supergiant, easily visible in the summer sky in the constellation Scorpius. It marks the heart of the Scorpion. Antares lies about 550 light-years from Earth. Its diameter is comparable to that of Betelgeuse, roughly 700 times that of the Sun. Antares has a small blue-white companion star slowly orbiting the much larger red supergiant. The name Antares comes from ancient Greek and means literally rival of Mars. The deep red color of Antares is so similar to the color of Mars that ancient observers compared the two regularly. Tonight, when Antares is visible in the sky, it still shows the same deep red color that ancient astronomers noted thousands of years ago. VY Canis Majoris, mentioned earlier in our Hypergiants chapter, is sometimes also classified as an extreme red supergiant. The boundary between large red supergiants and small red hypergiants is not always perfectly clear. Both phases involve a cool, extended outer atmosphere and slow, steady mass loss into the surrounding cosmic environment. Mu Cephei, the garnet star, is sometimes classified as a red supergiant rather than a hypergiant. Like Antares and Betelgeuse, it is visible to the unaided eye on a clear, dark night. Its deep red color is striking through any telescope. Of all the red supergiants visible from Earth, Mu Cephei is one of the most distinctively colored. Red supergiants form when a massive star, perhaps 8 to 30 times the mass of the Sun, exhausts the hydrogen fuel in its core. As the core contracts and grows hotter, the outer layers expand outward and cool. The star transitions from a hot blue main sequence star into a cool red giant. If the original mass is large enough, the expansion continues until the star becomes a true red supergiant. The interior of a red supergiant is far more complex than the relatively simple interior of the Sun. Multiple shells of nuclear fusion operate at different depths, each one producing different elements. The innermost shell may be fusing iron, the most stable element of all. Outer shells fuse silicon, oxygen, neon, carbon, and so on. Each shell is small compared to the vast outer atmosphere, but together they generate enormous luminosity. Red supergiants lose mass continuously. The wind from a typical red supergiant carries away the equivalent of one Earth mass every few thousand years, sometimes faster. Larger episodic eruptions can release more material in shorter periods. Over the lifetime of a red supergiant, the total amount of material released into space can be a significant fraction of the original stellar mass. The mass loss from red supergiants creates beautiful nebulae of cosmic dust around them. The dust forms when atoms in the stellar wind cool and condense at large distances from the star. The resulting cosmic dust shells can extend for many light years outward, slowly mixing with the surrounding interstellar medium across cosmic timescales. Red supergiants typically last only a few 100,000 years in this final phase before they reach the end of their evolution. The end usually comes as a core collapse supernova. The iron core, no longer producing energy, suddenly collapses inward. The outer layers rebound off the contracting core and are released into space at speeds of thousands of kilometers per second. After a red supergiant supernova, what remains in the very center is usually a neutron star, or sometimes a black hole. The outer layers continue expanding into the surrounding interstellar medium for thousands of years, eventually mixing with the cosmic environment. The chemical elements forged in the red supergiant interior become available for the next generation of stars and planets. Tonight, the famous red supergiants of our galaxy continue their patient stellar lives. Betelgeuse continues to shine its warm orange light across the winter sky. Antares continues to mark the heart of Scorpius. Mu Cephei continues to glow deep garnet red in the constellation Cepheus. Each one is slowly evolving toward its eventual cosmic transition. Each one will eventually become a memory in the history of the Milky Way. Now we will gently leave the cool red supergiants behind and turn toward stars at the opposite end of stellar mass, the brown dwarfs, the failed stars that almost crossed the threshold of stellar fusion. Brown dwarfs are sometimes called failed stars. Each one formed from a collapsing cloud of cosmic gas, just like an ordinary star, but each one stopped just short of becoming massive enough to ignite stable hydrogen fusion in its core. Without that sustained fusion, brown dwarfs do not shine in the way that ordinary stars do. They glow only faintly, primarily from the residual heat of their slow cosmic formation. The threshold between a brown dwarf and a true star sits at roughly 75 times the mass of the planet Jupiter. Above that threshold, a stellar object can sustain hydrogen fusion in its core for billions of years. Below it, the object is a brown dwarf. Brown dwarfs typically have masses between about 13 and 75 Jupiter masses. The first definitive brown dwarf was discovered in 1995. The object, called Gliese 229b, was found orbiting a small red dwarf star about 19 light-years from Earth. Detailed observations confirmed that it was much too cool to be a star, but slightly warmer than a planet would normally be. It marked the beginning of brown dwarf astronomy as a recognized field of study. Brown dwarfs are classified into spectral types based on their temperature and atmospheric composition. The L-type is warmer and shows iron and silicate clouds. The T-type is cooler and shows methane absorption. The Y-type is the coolest known, with temperatures sometimes below the freezing point of water. The Y dwarfs are barely warmer than the planet Jupiter itself. The atmospheres of brown dwarfs are remarkable. Despite being cool by stellar standards, They are still hot enough to support exotic chemistry. In an L-dwarf atmosphere, iron and silicate dust grains can form in clouds. In a T-dwarf atmosphere, methane molecules absorb particular wavelengths of infrared light. In a Y-dwarf atmosphere, water clouds can begin to form similar to those on a giant planet. The coolest known brown dwarf is WISE 0855-0714, located only about 7.5 light-years from Earth, making it one of our nearest cosmic neighbors. Its surface temperature is roughly 250 Kelvin, about -23 degrees Celsius, colder than the typical surface temperature of the planet Mars during winter. It is a remarkably cold stellar object. Brown dwarfs do briefly fuse some material in their early lives. Lithium and deuterium can fuse at lower temperatures than ordinary hydrogen, and brown dwarfs cross those temperature thresholds for relatively brief periods. After the early lithium and deuterium are exhausted, the brown dwarf simply cools quietly for the rest of its existence, slowly fading across billions of years. Astronomers can sometimes use the lithium test to determine whether a particular faint object is a low-mass star or a brown dwarf. Stars destroy their lithium quickly through nuclear processes. Brown dwarfs preserve some lithium because their interiors do not become hot enough to destroy it efficiently. Detecting lithium in the atmosphere of a small dim object is a strong sign that it is a brown dwarf. Brown dwarfs can have planetary atmospheres in many ways. Strong winds blow across the upper atmosphere, sometimes producing swirling cloud bands similar to those on Jupiter. Slow rotation patterns reveal the cosmic dynamics of the cool atmosphere. Some brown dwarfs even show aurora-like emission from charged particles entering their atmospheric layers, much as auroras occur on giant planets. Some brown dwarfs orbit in close binary systems with other brown dwarfs. These pairs orbit each other quietly, gradually losing energy through tidal interactions and slowly approaching closer over cosmic time. Some brown dwarf binaries have orbital periods of years to decades. Many will eventually merge into more massive cosmic objects. Brown dwarfs sometimes also orbit ordinary stars. They can be at distances ranging from very close to extremely far. Brown dwarf companions are sometimes found through direct imaging at large separations from their parent stars. They appear as faint warm objects in infrared images, distinguishable from background galaxies and other unrelated cosmic sources. The number of brown dwarfs in our Milky Way galaxy is uncertain but probably enormous. Estimates suggest there could be as many brown dwarfs as ordinary stars, or perhaps even more. Most of them are too cool and too dim to detect from Earth. Only the brightest, the closest, or the most easily separated from background sources are currently cataloged. Some brown dwarfs are not associated with any star at all. These free-floating brown dwarfs drift quietly through interstellar space on their own. They are sometimes called rogue brown dwarfs. Their motion through the galaxy is the slow result of small gravitational kicks they receive during their formation, sometimes from a passing nearby star. Brown dwarfs overlap conceptually with the largest gas giant planets. The boundary between a very massive planet and a low-mass brown dwarf is not perfectly sharp. Below 13 Jupiter masses, the object is generally classified as a planet. Above 13 Jupiter masses, brief deuterium fusion in early life makes the object a brown dwarf. Some objects sit very close to that boundary and are difficult to classify. Some of the youngest brown dwarfs are still forming in the dense molecular clouds of star-forming regions. The Ophiuchus and Taurus star-forming regions, both relatively close to Earth, contain numerous young brown dwarfs in their early stages of cosmic existence. These young brown dwarfs are warmer than older ones, but still much cooler than ordinary stars. The infrared sky is full of brown dwarfs that ordinary visible light telescopes cannot see. Surveys like the Wide Field Infrared Survey Explorer satellite, abbreviated WISE, have cataloged hundreds of brown dwarfs across the sky. Most brown dwarfs in our cosmic neighborhood have probably now been identified through such surveys. Tonight, brown dwarfs throughout our galaxy continue their long, quiet existence. They are not generating new energy in their cores. They are simply cooling slowly across deep cosmic time, fading from their warm L-dwarf youth to colder T-dwarf maturity to the very cold Y-dwarf phase that some of them have already reached. Some are still warming through their early lithium fusion. Others are nearly indistinguishable from giant planets. Now, we will move from the failed stars at the bottom of the stellar mass spectrum to a different family of stellar remnants entirely. The white dwarfs, the cooling cores left behind by stars more like our Sun. White dwarfs are the dense, glowing remnants of medium-sized stars. When a star like our Sun reaches the end of its life, it sheds its outer layers into a beautiful planetary nebula. What remains in the very center is the white dwarf, the exposed hot core of the former star, slowly cooling across cosmic time. A typical white dwarf has a mass comparable to that of the Sun, packed into a sphere about the size of the planet Earth. The density inside is enormous, about 1,000,000 times the density of water. A teaspoon of white dwarf material would weigh several tons here on the surface of our planet. The first white dwarf to be detected was Sirius B, the small companion to the bright nearby star Sirius. Sirius is the brightest star in the night sky, located about 8.5 light years from Earth. Sirius B is about 10,000 times fainter, but its mass and gravitational influence on Sirius A had been suspected for decades before it was finally directly observed. In 1915, the astronomer Walter Sidney Adams measured the spectrum of Sirius B and was able to confirm its small size and high temperature. The observation was an early triumph of astrophysics. The discovery confirmed that some objects in the universe could be far denser than ordinary matter, opening the way to understanding what was happening in the late stages of stellar evolution. Most white dwarfs are made primarily of carbon and oxygen. These are the products of helium fusion, the second nuclear fuel a star uses after hydrogen. The interior is in a special phase of matter where electrons have been stripped from their atoms and form a degenerate electron gas. The pressure from these electrons is what holds the white dwarf up against its own gravity. The maximum mass of a white dwarf is about 1.4 times the mass of the Sun. This limit was calculated by the Indian astrophysicist Subrahmanyan Chandrasekhar in 1930. Above this mass, the electron degeneracy pressure can no longer support the white dwarf, and the object would collapse into a neutron star or trigger a thermonuclear explosion. Chandrasekhar received the Nobel Prize in 1983 for this work. White dwarfs are extraordinarily hot when they first form. Surface temperatures of 100,000 Kelvin or more are common for very young white dwarfs. Over time, they cool steadily by emitting light into deep space. The cooling is gradual but inexorable. After a billion years, a typical white dwarf has cooled to about 10,000 Kelvin. After 10 billion years, perhaps to a few thousand Kelvin. The very oldest white dwarfs in our galaxy are now extraordinarily cool, with surface temperatures perhaps as low as 3,000 Kelvin. These ancient white dwarfs date back to the early days of the Milky Way, more than 10 billion years ago. They are some of the oldest objects in our galaxy that are still detectable, slowly fading across deep cosmic time. As a white dwarf cools, its interior eventually begins to crystallize. The carbon and oxygen atoms slowly arrange themselves into a regular crystalline lattice, much like the structure of a diamond. The largest white dwarfs may have crystalline cores hundreds of kilometers thick by the time they have cooled significantly. Some astronomers have called these objects cosmic diamonds, though the chemistry is more complex than that. Some white dwarfs pulsate. Their surface oscillates with periods of minutes to hours, producing small periodic variations in brightness. These pulsations occur in white dwarfs of particular temperature ranges, where ionization layers in the outer envelope create the conditions for instability. The pulsations let astronomers probe the deep interior of the white dwarf, much like seismology probes the interior of the Earth. Some white dwarfs are part of close binary systems, where matter from a companion star slowly accretes onto the white dwarf's surface. These accreting white dwarfs are sometimes called cataclysmic variables. The accreted material can briefly trigger small thermonuclear flashes on the white dwarf surface, producing what astronomers call novae. A nova is a brief brightening that fades over weeks to months. If a white dwarf accretes enough material to push its mass close to the Chandrasekhar limit, the entire object can suddenly undergo runaway thermonuclear fusion. The result is a type Ia supernova, one of the brightest events in the universe. The white dwarf is completely destroyed in the process, leaving no remnant behind. Its material is distributed across surrounding cosmic space. Type Ia supernovae are unusually consistent in their peak brightness. This consistency makes them extremely valuable for measuring cosmic distances. Astronomers calibrate their actual brightness from nearby examples, then compare to the apparent brightness of distant type Ia supernovae to measure how far away they are. This method led to the discovery of the accelerating expansion of the universe in the 1990s. White dwarfs are extremely common in our galaxy. About 97% of all stars in the Milky Way will eventually become white dwarfs. The total number of white dwarfs in our galaxy is roughly 10 billion. Most of them are quite faint, having cooled from their initial high temperatures over billions of years. They are scattered throughout the galactic disk and halo. White dwarf atmospheres are unusual. Most white dwarfs have very thin atmospheres dominated by either hydrogen or helium. Heavier elements rapidly sink toward the interior under the white dwarf's strong gravity, leaving the surface chemically simple. Sometimes, a thin layer of gas accreted from interstellar space mixes briefly into the upper atmosphere before sinking down. Some white dwarfs are surrounded by faint debris disks. These disks are believed to be the remnants of planetary systems that the white dwarf inherited from the original star. As asteroids and small rocky bodies pass too close, the white dwarf's strong gravity tears them apart. The debris settles into a slow, gentle disk around the cosmic remnant. Some of the matter eventually accretes onto the white dwarf surface, briefly contaminating its atmosphere. Tonight, white dwarfs throughout our galaxy continue their slow, patient cooling across cosmic time. The youngest are still extremely hot. The middle-aged ones are quietly fading from white into yellow, into orange, into red. The oldest are nearly invisible, slowly approaching a state of cosmic blackness that will only be reached far in the future of the universe. Their slow cooling is one of the most patient processes in the cosmos. Now, we will move from the cooling stellar remnants to a fascinating family of variable stars whose changes in brightness have helped astronomers measure the size of the entire cosmos, the Cepheid Variables. Cepheid variable stars pulse in size and brightness with a steady cosmic rhythm. Each one expands and contracts on a regular cycle, with periods ranging from a few days to a few months. Each pulsation produces a smooth wave of brightness, rising slowly to a peak, then falling slowly back to the minimum, then rising again. Tonight, countless Cepheids across the galaxy are quietly continuing their cosmic pulsations. First known Cepheid variable Delta Cephei was discovered in 1784 by the astronomer John Goodrick. Goodrick was a young deaf astronomer in York, England. He had already identified the variable nature of the star Algol. Now he noticed that Delta Cephei in the constellation Cepheus was brightening and dimming on a regular cycle of about 5 1/3 days. Tonight, Delta Cephei is still pulsating on the same schedule. In 1908, the astronomer Henrietta Swan Leavitt made one of the most important discoveries in the history of astronomy. Working at Harvard College Observatory, she was studying photographic plates of the Small Magellanic Cloud, a small companion galaxy to the Milky Way. She noticed that brighter Cepheids in the cloud had longer pulsation periods, and fainter Cepheids had shorter periods. Leavitt's observation revealed what is now called the period-luminosity relation. The longer a Cepheid's pulsation period, the more luminous the star is in absolute terms. By measuring the period of a Cepheid, astronomers can deduce its true luminosity. By comparing that to its apparent brightness, they can calculate its distance. Cepheids became the first reliable cosmic distance markers. This discovery transformed astronomy. Until Cepheids could be used as cosmic distance markers, no one knew how far away the various nebulae and clusters in the sky actually were. Within a few decades, Edwin Hubble used Cepheids in the Andromeda Nebula to prove that Andromeda was a separate galaxy outside the Milky Way. The size of the known universe expanded enormously almost overnight. Cepheid pulsations are caused by a phenomenon called the Kappa mechanism. Deep in the outer atmosphere of the star, a layer of partially ionized helium acts as a kind of valve. When the layer is compressed, it absorbs more radiation. When it expands, it releases that radiation outward. The cycle of compression and expansion drives the steady pulsation of the star, like the slow, gentle breathing of a vast cosmic body. The light curve of a Cepheid is asymmetric. The rise to maximum brightness happens quickly. The fall to minimum brightness happens more gradually. Astronomers can identify a Cepheid simply by the characteristic shape of its light curve. The asymmetry tells them the precise stage of pulsation, even from a single observation. Polaris, the famous North Star, is itself a Cepheid variable. Its pulsations are unusually small in amplitude, only about 3% variation in brightness over a period of about 4 days. Polaris is so close to Earth, only about 400 light-years away, that it is one of the nearest Cepheids known. The small pulsations of Polaris are at the very limit of human visual detection. Cepheids are divided into two main types based on their stellar populations. Type I Cepheids, also called classical Cepheids, are young massive stars in the disks of spiral galaxies. Type II Cepheids, also called W Virginis stars, are older, lower-mass stars typically found in globular clusters and the galactic halo. The two types have slightly different period luminosity relations. Cepheid variables are among the largest pulsating stars known. A typical Cepheid has a radius of 100 to several hundred times that of the Sun. Despite this enormous size, the entire star pulsates as one coherent body, with all parts of the surface rising and falling together in slow cosmic rhythm. Astronomers have used Cepheids to measure distances to galaxies up to about 100 million light-years away. Beyond that distance, individual Cepheids become too faint to detect, and astronomers turn to other distance methods, including type Ia supernovae, to map even further into deep cosmic space. The Cepheid scale is just the first rung of the cosmic distance ladder. Rarest stars are sometimes grouped near Cepheids in stellar physics, though they are technically a different type of pulsating star. Rarest stars are old low-mass horizontal branch stars in globular clusters. They pulsate with periods of less than 1 day. They are also useful as distance markers, especially within our own galaxy and its globular clusters. Some unusual Cepheid-like stars exist on the boundaries of the standard categories. Beat Cepheids show two simultaneous pulsation periods, producing complex beat patterns in their brightness. Anomalous Cepheids occur in some old stellar populations, but with shorter periods than expected. Each variant offers a window into the detailed physics of stellar pulsation. The Hubble Space Telescope has been particularly important for Cepheid astronomy. Its sharp images allow astronomers to identify individual Cepheid variables in galaxies tens of millions of light-years away. The careful measurement of these distant Cepheids has refined our knowledge of the Hubble constant, the rate at which the universe is expanding to extraordinary precision. Cepheid stars exist in a relatively brief phase of stellar life. They are crossing what astronomers call the instability strip on the Hertzsprung-Russell diagram, a particular region of stellar temperature and luminosity where pulsations naturally occur. A typical star spends only a few 100,000 years in this phase. After that, the star moves out of the instability strip and stops pulsating. The classical Cepheids in our galaxy are typically 4 to 20 times the mass of the Sun. They are massive stars in the late stages of their lives, having already left the main sequence and entered the red supergiant region or beyond. Some Cepheids will eventually become Wolf-Rayet stars or red supergiants. Others will return through the instability strip multiple times before reaching their final stellar fate. Tonight, countless Cepheid variables across the cosmos continue their gentle cosmic pulsations. Each one is a precise stellar clock that astronomers can use to map the distance scale of the universe. Each one is a slowly breathing cosmic body, expanding and contracting on its own steady schedule. Each one is a piece of the precise calibration that lets us understand the size and age of the cosmos itself. Now, we will leave the steady pulsing rhythm of Cepheids and turn toward stars that exist in pairs, the binary stars, where the gravitational dance of two stellar bodies creates phenomena that no single star could produce on its own. Most stars in the universe are not alone. They exist as binary or multiple star systems, gravitationally bound to one or more companions. Estimates suggest that perhaps half or more of all stars in our galaxy are part of binary systems. The Sun is a relatively rare solitary star. Most of the stars you can see in the night sky are actually pairs or groups when examined more closely. Binary star systems form when a single collapsing molecular cloud fragments into two or more pieces during the early stages of star formation. Each fragment contracts to form its own star, but the resulting stars remain gravitationally bound. After a few million years of settling, the new binary system reaches a stable orbital configuration that can persist for billions of years. Astronomers classify binary stars based on how they are detected and how they orbit. Visual binaries are pairs that can be seen as separate points of light through a telescope. Spectroscopic binaries are too close together to be visually separated, but their orbital motion is revealed by Doppler shifts in their spectra. Eclipsing binaries are pairs whose orbital plane is aligned with our line of sight, so the stars periodically pass in front of each other. Algol, in the constellation Perseus, is the prototype eclipsing binary. Its name comes from Arabic and means literally the demon star. Ancient observers noticed that Algol mysteriously dimmed and brightened on a regular schedule. The reason was finally understood in 1783 by John Goodricky. Algol consists of two stars orbiting each other every 2.8 days. Each orbit, the dimmer star passes in front of the brighter one, briefly reducing the total light. Mizar, in the handle of the Big Dipper, is a famous visual binary. The two main stars of the Mizar system can be separated through any small telescope, and even with the unaided eye on a clear, dark night. The slightly fainter companion star Alcor sits nearby. When studied more carefully, both Mizar A and Mizar B turn out to be themselves spectroscopic binaries. The full Mizar system contains 6 stars, all gravitationally bound. Binary stars come in a wide range of separations. Some pairs orbit each other in less than a day, with the two stars almost touching. Others orbit on cycles of thousands or millions of years, with vast cosmic distances between them. The shape of the orbit can be circular or extremely elongated, depending on the dynamic history of the system. In close binary systems, the two stars can interact in interesting ways. Each star has a region around it called the Roche lobe, within which its gravity dominates. If one star expands enough to fill its Roche lobe, material from the outer atmosphere can flow toward the companion star through a narrow point called the inner Lagrangian point. This kind of gentle mass transfer reshapes the evolution of both stars. Detached binary systems are pairs in which neither star fills its Roche lobe. Each star evolves more or less independently, like a solitary star. Semi-detached binaries are pairs in which one star fills its Roche lobe and is transferring mass to its companion. Contact binaries are extreme cases in which both stars fill their Roche lobes and share a common envelope of stellar material. Some of the most common contact binaries are the W Ursae Majoris stars. These pairs share a common envelope of stellar material that surrounds both stellar cores. Their orbital periods are typically less than half a day. Their brightness changes continuously and smoothly as the two stars orbit, never showing a clear flat minimum because the system is essentially one peanut-shaped cosmic body. Cataclysmic variables are binary systems containing a white dwarf accreting matter from a companion star. The accretion can be steady or episodic. When enough material has accumulated on the white dwarf, brief thermonuclear flashes called novae can occur, briefly brightening the system. Some cataclysmic variables are relatively stable. Others are extremely variable, brightening and fading on irregular schedules. X-ray binaries are systems where the accreting object is a neutron star or black hole instead of a white dwarf. The strong gravity of these compact objects compresses the accreting material to extremely high temperatures, producing powerful X-ray emission. X-ray binaries are some of the brightest X-ray sources in the entire sky. In some binary systems, mass transfer eventually reverses one of the stars. This is sometimes called the Algol paradox. The original, less massive companion star can expand and overflow its Roche lobe, transferring mass to the original, more massive primary star. After this exchange, the originally more massive star is now actually less massive than its companion, even though it began the more massive of the two. Some binary systems eventually merge. After billions of years of slow tidal evolution, the two stars approach each other ever more closely until they finally come into direct contact and combine into a single object. The resulting merged star can be more massive than either of the original components and may show unusual properties resulting from the combination of two stellar lifetimes worth of internal evolution. Binary stars containing two neutron stars or two black holes can produce gravitational wave emission. As the two compact objects orbit, they radiate gravitational waves into the surrounding cosmic spacetime, gradually losing orbital energy. Over millions of years, the orbit shrinks. Eventually, the two compact objects spiral together and merge in a brief burst of gravitational radiation that has been detected by observatories on Earth. Binary stars also include systems where one component has already become a stellar remnant. White dwarf binaries with main sequence companions are common. Neutron star binaries with massive companions are responsible for some of the brightest X-ray sources in the galaxy. Black hole binaries with normal star companions reveal themselves through the X-ray emission of accreting matter. Tonight, countless binary star systems throughout our galaxy continue their slow cosmic dances. Some have orbits of mere hours, others have orbits of millions of years. Some are exchanging material continuously, some are simply orbiting in cosmic patience without any interaction. All of them are doing what binary stars do, moving together through the long, quiet history of the universe. Now, we will move from the general family of binary stars to one of the most unusual and dramatic kinds of binary systems, the Black Widow pulsars, where a neutron star slowly evaporates its companion across cosmic time. Black Widow pulsars are among the most unusual binary systems in the universe. Each one consists of a rapidly rotating millisecond pulsar paired with a very low-mass companion star. The intense radiation and stellar wind from the pulsar slowly evaporates the companion across cosmic time. The companion gradually loses mass, sometimes shrinking to near nothing across the long, quiet stretch of stellar lifetime. The first Black Widow pulsar discovered was PSRB 1957+20, found in 1988 in the constellation Sagitta. The pulsar rotates 622 times per second. its companion star is only about 2% of the mass of the Sun. The companion is so small and lightweight that it is more like a low-mass brown dwarf than an ordinary stellar body. The name Black Widow Pulsar is a reference to the spider species, in which the female sometimes consumes the male after mating. In the case of these binary systems, the pulsar is slowly evaporating its companion through powerful radiation and an outflow of energetic particles. The companion loses material continuously across cosmic time, reducing its mass over millions of years. The companion star in a typical Black Widow system is heavily ablated. Its outer atmosphere is constantly being stripped away by the pulsar wind. Material flows outward from the companion, forms a slowly expanding cosmic cocoon around the binary system, and eventually disperses into the surrounding interstellar medium. Some Black Widow companions have been almost completely evaporated, leaving only a small core of degenerate matter. As the pulsar evaporates the companion, the cocoon of expelled material can sometimes block our view of the pulsar from Earth. When the companion is between us and the pulsar, the radio pulses from the pulsar are temporarily eclipsed. These eclipses last for a few minutes around each conjunction of the binary orbit. Outside the eclipses, the pulses arrive normally. Astronomers have cataloged dozens of Black Widow pulsars in our galaxy. Some are isolated, some are in globular clusters where the dense stellar environment makes binary interactions more frequent. Globular clusters are particularly rich in millisecond pulsars in general, and a significant fraction of those are Black Widow systems. A related class of binary system is called the redback pulsar. Redbacks are similar to Black Widows in that they involve a millisecond pulsar paired with a low-mass companion. But in redback systems, the companion is somewhat more massive, typically around 1 or 2/10 of a solar mass. The companion is being ablated, but more slowly than in a Black Widow. Both classes are sometimes grouped together as spider pulsars. Black Widow pulsars are believed to have evolved through a long history. Originally, the pulsar was a slow neutron star. Then, billions of years ago, the now evaporating companion was a normal star that expanded into a red giant. Material from the companion flowed onto the neutron star, gradually accelerating its spin to millisecond rates. After this recycling phase, the pulsar emerged as an extremely fast rotator, and the relationship reversed. Now the pulsar evaporates the companion that once spun it up. Some Black Widow pulsars have been observed to have very strong gamma-ray emission, in addition to their radio pulses. The gamma rays come from charged particles accelerated near the pulsar, interacting with the magnetic field and the cocoon of evaporated material. Black Widow systems are some of the brightest gamma ray sources in the entire sky. Despite their dramatic name, Black Widow pulsars are quiet and patient on a human timescale. The evaporation of the companion takes place over millions to billions of years. There's no sudden cosmic event. The companion simply continues to shrink slowly, year after year, century after century, far longer than human history. The whole process unfolds in cosmic patience. Some Black Widow systems may eventually finish the evaporation entirely. After enough time, the companion will be reduced to nothing, leaving a solitary millisecond pulsar with no surviving companion. Astronomers have suggested that some isolated millisecond pulsars in our galaxy may be the leftover remnants of Black Widow systems that completed the evaporation process. The compact binary nature of black widow systems makes them useful for studying gravity in extreme conditions. The orbital motion is faster than in most binaries, and the gravitational field of the millisecond pulsar is strong. Precise timing of the pulses can reveal subtle effects predicted by general relativity, helping astronomers test the deepest theories of cosmic physics. Some black widow companions show unusual brightness variations because of the heating from the pulsar. The side of the companion facing the pulsar is much hotter than the opposite side. As the companion orbits, different sides become visible from Earth, producing slow changes in the companion's apparent brightness. The hot side can be many thousands of degrees warmer than the cool side. In some particularly extreme black widow systems, the companion is being heated to such high temperatures that it briefly resembles a small bright star, even though its mass is far below the threshold for stellar fusion. The heating is not generating energy through fusion. It is purely the absorption of radiation from the rapidly rotating pulsar nearby. Black widow pulsars are thought to be relatively rare among binary systems, but may have been more common in earlier cosmic eras. The formation of millisecond pulsars requires the interaction of a neutron star with a binary companion, and the right conditions for that interaction have evolved over the long history of our galaxy. Different generations of stars have produced different proportions of these unusual systems. Tonight, the small population of black widow pulsars in our galaxy continues quietly. Each pulsar is rotating at extraordinary rates, releasing its faint cosmic beams. Each companion is slowly losing material into the surrounding cosmic environment. The whole process is patient and unhurried, taking place across cosmic timescales beyond imagining. Now we will leave the slow, gentle drama of black widow systems and turn toward one of the most famous individual stars in the southern sky, Eta Carinae, the most volatile known star in our cosmic neighborhood. Eta Carinae is one of the most famous and most volatile stars known to astronomers. It lies about 7,500 light-years away from Earth, in the southern constellation Carinae. It is not a single star, but actually a binary system, with a primary star of perhaps 100 solar masses and a smaller but still massive companion. Together, the system is one of the most luminous stellar configurations in our galaxy. In the year 1843, Eta Carinae underwent a remarkable cosmic event known as the Great Eruption. Over a period of years, the star briefly became the second brightest star in the entire night sky, outshone only by Sirius. This was extraordinary because Eta Carinae is far more distant than Sirius. The intrinsic brightness of Eta Carinae during this eruption was about 100 million times that of the Sun. The Great Eruption ejected a vast amount of material, perhaps 10 or 20 solar masses worth, outward into the surrounding cosmic space. This released material formed the beautiful structure now visible around Eta Carinae called the Homunculus Nebula. The nebula is shaped like two large lobes connected at the middle, with a smaller equatorial disk between them. The Homunculus Nebula has been imaged in extraordinary detail by the Hubble Space Telescope and other instruments. It glows with the warm light of dust, illuminated by Eta Carinae itself. The two lobes are expanding outward at roughly 650 kilometers per second. As the nebula grows over time, the structure becomes ever more spectacular, slowly inflating across cosmic distances. Eta Carinae did not destroy itself in the Great Eruption. Despite ejecting an enormous amount of mass, the underlying binary star system survived. The star is still there tonight. It still releases enormous amounts of energy. It is still considered one of the candidates for a future supernova or hypernova in our galaxy, perhaps in the next million years or so. In the 1890s, Eta Carinae underwent a smaller eruption, sometimes called the Lesser Eruption. This second eruption was less dramatic than the first, but still significant. It added more material to the surrounding nebula. The reasons for these episodic eruptions are still being studied. They may be related to interactions between the two stars in the binary system, or to instabilities in the outer atmosphere of the primary star. Eta Carinae is the prototype of a class of unusual stars, sometimes called luminous blue variables, or LBVS. These are massive hot stars that show occasional dramatic outbursts. Several other LBVS are known in our galaxy and in nearby galaxies. P Cygni in the constellation Cygnus is one such example. G Carinae is another. Each one shows its own pattern of slow and irregular cosmic activity. P Cygni in the constellation Cygnus is itself a famous luminous blue variable. P Cygni had a major eruption in 1600. Before that eruption, the star was invisible to the unaided eye. After the eruption, it became prominent in the night sky. P Cygni is still bright tonight, sitting calmly in its slow recovery phase. The characteristic spectral profile of P Cygni, emission with blue-shifted absorption, has been named after the star and is now used to identify similar phenomena in other cosmic objects. G Carinae is another famous luminous blue variable, located about 20,000 light-years from Earth. G Carinae is surrounded by a delicate nebula of cosmic dust and gas, ejected during a previous outburst. The nebula is being illuminated from within by the central star, producing a quietly beautiful structure in the southern sky. HD 5980 is a particularly interesting double system in the Small Magellanic Cloud. Both stars are luminous blue variables, making it one of the few known binary LBV systems. Together, they make a remarkably luminous configuration. The system has shown variable activity over the years, with both components contributing to the cosmic spectacle. The mechanism behind the eruptions of luminous blue variables is still being studied. The leading idea involves a phenomenon called the Eddington limit. At extreme luminosities, the radiation pressure from a star's outer layers can briefly overcome the gravitational binding of the atmosphere, causing material to be released outward. This may happen during periods of internal instability, when the star's outer atmosphere becomes temporarily unbound. Despite their dramatic eruptions, luminous blue variable stars spend most of their time in relatively quiet phases. The eruptions are episodic events separated by decades, centuries, or longer. Tonight, most known LBVs are in quiet phases. They continue to shine brightly, but without the dramatic outbursts that occasionally remind astronomers of their volatile nature. Eta Carinae is sometimes considered a precursor to a supernova or hypernova. The combination of extreme mass, hot temperature, fast rotation, and ongoing instability suggests the star is approaching the end of its evolution. When Eta Carinae eventually does reach its final cosmic transition, the resulting supernova may be one of the brightest events in the human history of astronomy. But the timing is uncertain. It may happen in the next few thousand years or perhaps a million years from now. If Eta Carinae produces a supernova or hypernova, the consequences for Earth would be limited. At 7,500 light-years, the star is far enough away that any radiation reaching us would be attenuated to safe levels. But the visual spectacle would be enormous. For weeks or months, Eta Carinae would briefly become brighter than the full moon, visible during daylight hours, dominating the southern sky. Other massive volatile stars in our galaxy include WR104, WR124, and several others previously mentioned in our Wolf-Rayet chapter. The Wolf-Rayet phase and the luminous blue variable phase are sometimes connected. Some massive stars may pass through both phases on their way to a final cosmic transition. Tonight, Eta Carinae continues to shine in the southern sky. Its surrounding homunculus nebula continues to expand. Its hidden binary partner continues to orbit. The system continues to evolve slowly toward its eventual transformation. Across the rest of our galaxy, other luminous blue variables continue their own slow, patient evolution, each one writing its own cosmic story across deep stellar time. Now, we will move from the volatile luminous blue variables toward an even more energetic phase of stellar evolution, the hypernovae, which mark the final transformation of the most massive stars in the cosmos. Hypernovae are exceptionally energetic stellar transformations. A hypernova is essentially a particularly powerful supernova, releasing several to 10 times more energy than an ordinary core collapse supernova. They mark the final transition of some of the most massive stars in the universe, typically those with progenitor masses of 40 to 100 solar masses or more. The progenitors of hypernovae are usually thought to be Wolf-Rayet stars. By the time these massive stars reach the hypernova phase, they have already shed most of their outer hydrogen envelope through the long Wolf-Rayet stellar wind. What remains is a hot helium and carbon-rich core supporting fusion in multiple shells. When the iron core finally collapses, the resulting transformation is unusually energetic. During a hypernova, the collapsing iron core forms either an unusually massive neutron star or, more commonly, a black hole. The black hole forms because the core mass is too large for any neutron degeneracy pressure to support. The compact remnant pulls in surrounding material at high speeds, releasing enormous gravitational energy as cosmic radiation. Hypernovae are believed to be connected with long-duration gamma-ray bursts. A long GRB is a brief but intense burst of gamma rays lasting several seconds to minutes, observed from distant sources across the universe. Long GRBs are now understood to be produced by hypernovae, specifically by the relativistic jets that emerge from the rotating black hole at the center of the dying star. The relativistic jets of a hypernova move outward at nearly the speed of light. They punch through the outer layers of the dying star and emerge into surrounding space. As they travel through the cosmic medium, they emit gamma rays along the direction of the jet. From Earth, we only see the gamma ray burst if one of the jets happens to be pointed approximately in our direction. After the initial gamma ray burst fades, the rest of the hypernova continues to brighten. Over the following days and weeks, the cosmic optical light from the expanding stellar material reaches its peak. The light curve of a hypernova is similar to that of an ordinary supernova, but the peak brightness is several times higher, reflecting the larger total energy of the event. One of the most famous hypernovae was SN 1998 BW, observed in 1998. This event in a distant galaxy was associated with a long gamma-ray burst, providing the first strong observational evidence that long GRBs and hypernovae are connected. The peak brightness of SN 1998 BW was about 10 times brighter than a typical supernova. Pair instability supernovae are an even more extreme form of stellar transformation. They occur in extremely massive stars, perhaps 140 to 200 solar masses or more, with relatively low metal content. In these stars, the core temperature reaches such high values that the radiation pressure can produce electron-positron pairs, which briefly remove energy from the core and trigger a runaway thermonuclear release. Pair instability supernovae are believed to leave no remnant behind. The entire star is converted to expanding cosmic material with no neutron star or black hole forming at the center. These events are thought to be much rarer than ordinary supernovae or hypernovae, and they may have been more common in the early universe when the first generation of stars contained essentially no heavy elements. SN 2007 BI, observed in 2007 in a distant galaxy, is one of the candidate pair instability supernovae. The event was extraordinarily luminous, brighter than typical hypernovae. The exact interpretation is still debated by astronomers, but pair instability remains a leading possibility for explaining its unusual cosmic properties. Hypernovae and pair instability supernovae are particularly important in the chemical evolution of galaxies. Each event releases vast amounts of heavy elements into surrounding cosmic space: iron, nickel, calcium, and many others. These elements eventually mix with the surrounding interstellar medium and become part of new generations of stars and planets, contributing to the chemical richness of the cosmic environment. Long gamma-ray bursts are extremely rare in our galaxy. The conditions required for a hypernova to produce a long GRB happen only once every hundreds of thousands of years in any given galaxy on average. The events we detect from Earth come from very distant galaxies across the universe. Long GRBs are visible across cosmological distances precisely because they are so energetic. Some hypernova candidates have been observed to involve unusual progenitor systems. For example, the collapsor model proposes that the hypernova progenitor must rotate rapidly with a large angular momentum carried into the collapsing core. This rapid rotation enables the formation of relativistic jets and the production of a long gamma-ray burst alongside the hypernova brightening. Detection of hypernovae has improved dramatically with modern surveys. Wide-field telescopes now scan large portions of the sky every night, looking for sudden brightening events. When a candidate is identified, follow-up observations help characterize the event and determine whether it represents a hypernova, an ordinary supernova, or some other cosmic phenomenon. Several hypernovae are typically detected each year. Hypernovae and the related long gamma-ray bursts have been used to probe the early universe. Because they are so bright, hypernova events at extreme cosmological distances can be detected from Earth. Each one provides a snapshot of star formation and stellar mass at the era when the hypernova occurred, sometimes billions of years in the past, when the universe was much younger. Tonight, somewhere in the vast cosmos, hypernovae are happening. Most of them are too distant for us to detect immediately. The light from some will eventually reach Earth after journeys of millions or billions of years. Each one represents the final transformation of one of the rarest and most massive stars in the universe, ending its life in one of the most energetic events possible in cosmic physics. Now, we will move from the most energetic stellar transformations to a quieter and more subtle category, the carbon stars, helium stars, and other unusual stars defined by their unusual chemical composition. Some stars in the universe have unusual chemical compositions in their atmospheres. They are not classified by their mass or luminosity, but by the particular elements that dominate their visible light. Among the most famous of these chemically unusual stars are the carbon stars, the helium stars, and the S-type stars. Each one offers a window into stellar evolution and the slow recycling of cosmic chemistry. Carbon stars are red giants whose atmospheres contain more carbon than oxygen. In a typical red giant, oxygen is the more abundant element. The chemical balance of carbon and oxygen affects the molecules that can form in the cool outer atmosphere. In carbon stars, carbon-bearing molecules dominate, including carbon monoxide, methylidyne, and various forms of cosmic soot. Rarest is one of the most famous carbon stars, located about 1,300 light-years from Earth in the constellation Lepus. It is sometimes called Hind's Crimson Star, after the astronomer J.R. Hind, who described it in 1845. The carbon-rich atmosphere of Rarest filters out blue light efficiently, giving the star its remarkable deep crimson color when seen through a telescope. V Hydrae is another famous carbon star, known for its unusual variability and complex outflow patterns. Astronomers have observed V Hydrae releasing material in slow, gentle bursts every few years, in patterns suggesting that it has a small, undetected binary companion shaping the outflows. Each release contributes to the elaborate cosmic structures forming around the central carbon star. Helium stars are an unusual category of star whose visible atmosphere is dominated by helium rather than the usual hydrogen. They are believed to be late evolutionary stages of certain types of stellar systems. In some cases, the original hydrogen envelope was stripped away by mass transfer to a binary companion. In other cases, the stripping was the result of strong stellar winds during an earlier evolutionary phase. Some helium stars are extreme. The hot subdwarf O stars and B stars are blazingly hot, with surface temperatures up to 100,000 Kelvin and beyond. Their light is dominated by ultraviolet radiation. They are sometimes found in the cores of planetary nebulae before the central star transitions to a white dwarf. Other helium stars are cooler, slowly transitioning into related stellar phases. S-type stars are another chemically unusual category. They are red giants in a peculiar chemical state where the relative abundances of carbon and oxygen are nearly equal. Their atmospheres show absorption lines from heavy elements like zirconium, technetium, barium, and yttrium. These elements are produced by slow neutron capture in the interior of the star, then dredged to the surface by convection. The presence of technetium in some S-type stars is particularly interesting. Technetium has no stable isotope. The longest-lived form has a half-life of only about 4 million years. The very presence of technetium in a stellar atmosphere therefore proves that the element is being produced inside the star in real time. then dredged to the surface within the past few million years. It is direct evidence of nuclear processes happening in the deep interior. Barium stars are a related category, though slightly different. They are giant stars whose atmospheres contain unusually high abundances of barium and other heavy elements. The barium was probably not produced by the star itself. Instead, the star inherited the barium from a now-vanished binary companion that produced the elements during its own asymptotic giant branch phase. Lithium-rich red giants are another unusual category. Most red giants destroy their lithium quickly through nuclear processes, but some red giants have been found with anomalously high lithium abundances, sometimes hundreds of times higher than expected. The reasons are still being studied. Mixing processes during the late stages of stellar evolution may briefly produce lithium that has not yet had time to be destroyed. Iron stars, in the theoretical sense, are the predicted end state of stars in the very far cosmic future. After unimaginable stretches of time far longer than the current age of the universe, all elements in old white dwarfs may slowly transmute into iron through quantum tunneling and other slow processes. The white dwarf would then become a true iron star, a sphere of nearly pure iron in cosmic space. Mercury-manganese stars are unusual hot stars whose atmospheres show enhanced abundances of mercury and manganese. The atmospheres are believed to be highly stratified, with diffusion separating elements based on their gravitational and radiation interactions. Heavier elements like mercury settle to particular atmospheric layers where they remain visible in the stellar spectrum. Cool R-type carbon stars are sometimes confused with carbon stars in general, but are distinguished by their slightly different evolutionary origins. Some R-type carbon stars are believed to come from binary mass transfer that brought carbon-rich material to the visible atmosphere. Others may be produced by particularly slow forms of stellar evolution that allow carbon to dredge up unusually efficiently. All these chemically unusual stars contribute to the slow long-term evolution of the cosmic chemistry. Each one releases its unusual atmospheric composition into surrounding space through stellar wind. The chemistry then mixes with the broader interstellar medium, contributing to the elemental composition of future generations of stars and planets across cosmic time. The diversity of chemically unusual stars reminds us how rich and varied stellar evolution can be. The standard picture of star formation and stellar evolution is correct in broad outline, but the details produce countless variations. Each chemically unusual star tells a slightly different story of stellar life, of binary interactions, of internal mixing, of unusual evolutionary pathways unique to that particular cosmic body. Tonight, the chemically unusual stars across our galaxy continue their quiet existence. Each one is slowly releasing its unique chemical signature into the surrounding space. Each one is participating in the long, slow cosmic recycling of matter that began with the first stars billions of years ago and continues into the deep future of the universe. Now, we will move from the chemically unusual stars to a category that exists primarily in theory, the exotic stars that may or may not exist somewhere in the universe, but whose hypothetical properties stretch the limits of physics. Beyond the directly observed categories of stars, theoretical physics has imagined several other types of stellar objects. Some of these may exist somewhere in the universe but have not yet been detected. Others may exist only in equations, awaiting future experiments and observations to confirm or deny their reality. Together, they remind us how much of cosmic physics remains to be explored. Quark stars are among the most discussed theoretical objects. The idea is that deep inside a sufficiently dense neutron star, the neutrons themselves may dissolve into their constituent quarks. The quarks then form a stable configuration of free quark matter, more compact than any neutron star but less compact than a black hole. Such a star would be smaller than a typical neutron star, but with similar mass. The strange matter hypothesis is a related theoretical idea. It proposes that the most stable form of matter at extreme densities is not ordinary nuclear matter, nor pure quark matter, but a special configuration containing roughly equal numbers of up, down, and strange quarks. If true, then any sufficiently dense neutron star might convert spontaneously to strange matter, becoming what astronomers call a strange star. If strange matter exists, it could be more stable than ordinary nuclear matter. A small piece of strange matter might convert any ordinary matter it touches into more strange matter. This raises an interesting cosmic question. If strange matter is stable, why does ordinary matter still exist in our universe? Various ideas have been proposed, but the question remains open in current cosmic physics. Boson stars are another theoretical category of stellar object. The idea proposes that under certain quantum conditions, a self-gravitating cloud of bosonic particles could form a stable cosmic body, supported against gravity not by ordinary thermal pressure, but by quantum effects called the Heisenberg uncertainty principle. The boson stars could in principle exist with a wide range of masses, from very small to very large. If boson stars exist, they could be a candidate for some forms of dark matter in the universe. Their cosmic gravitational effects would be similar to those of ordinary stars, but they would not emit any light. Astronomers might detect them indirectly through their gravitational influence on surrounding matter, or through gravitational lensing of distant background light. Preon stars are yet another theoretical possibility. They would be even more compact than quark stars. The idea is that quarks themselves might be made of smaller particles called preons, and at extreme density, preons might form a stable stellar object. Preons themselves are not directly confirmed by experiment, so the existence of preon stars is doubly speculative. Q stars are theoretical stellar objects supported by the quantum properties of certain unusual fields. They share some properties with both boson stars and ordinary cosmic objects, but exist only in theoretical scenarios where particular extensions of physics turn out to be correct. Their hypothetical existence has been studied as a possible explanation for some unexplained cosmic phenomena. Electroweak stars are theoretical objects that would be supported by the electroweak interaction operating at extreme densities. Inside such a star, ordinary matter would not exist as we know it. Instead, fundamental particles would interact through the unified electroweak force. The electroweak stars are predicted to exist briefly during the late stages of stellar collapse before the final transformation to a black hole. Dark stars are another theoretical possibility, particularly important in the early universe. The idea proposes that the first generation of stars might have been powered not by ordinary nuclear fusion, but by the annihilation of dark matter particles inside a dense gravitationally bound cloud. Such dark stars could have been very different from any star we currently observe, much larger, much cooler, and powered by an entirely different process. Theoretical predictions for these various exotic objects come from extending the equations of physics into regimes that have not been directly tested. Most predictions involve combining quantum mechanics and general relativity in ways that go beyond confirmed experimental knowledge. This is one reason why exotic stars remain theoretical for now. The experiments needed to confirm or rule them out are extraordinarily difficult. Some theoretical stars are unstable. Their predicted lifetimes are too short for them to be detected through normal observations. Other theoretical stars might be very stable but produce only subtle observational signatures, requiring extremely sensitive instruments to detect. The lack of confirmed detections of any exotic star may simply reflect the limitations of current cosmic observational techniques. Some astronomers search actively for exotic stars by looking for unexplained signals in pulsar timing data, gravitational wave observations, or X-ray emissions from neutron star surfaces. Each careful study refines the parameters of what could exist and where. Even null results, finding nothing where exotic objects might have been, are valuable in narrowing down theoretical possibilities. In the very far future, when the universe has cooled and aged for far longer than its current age, exotic stars may become more common. As ordinary matter slowly transforms through quantum tunneling, the cosmic environment may favor different stable configurations. The far future cosmos may contain stellar objects that are extremely rare or impossible in the present epoch. The study of exotic stars is also valuable independently of whether they actually exist. Theoretical work on these hypothetical objects refines our understanding of fundamental physics. The constraints derived from non-detection help test theories of quantum mechanics, general relativity, and the unification of fundamental forces. Even if exotic stars do not exist anywhere in the cosmos, exploring them rewards us with deeper understanding. Tonight, somewhere in the vast cosmos, exotic stars might be quietly existing, or they might not exist at all, or some might exist while others do not. The answer awaits future observations, future theoretical work, and the patient long-term progress of cosmic physics. The universe itself is the best laboratory for such investigations, and we are gradually building the instruments to read its answers. Now, we will move from the theoretical and exotic toward our final chapter, the cosmic cemeteries of the universe, where stellar remnants accumulate across deep cosmic time. Across the universe, the long history of stellar life and death has produced vast accumulations of stellar remnants. Old globular clusters contain ancient white dwarfs and neutron stars going back to the very early epochs of cosmic history. The galactic halo holds dark matter and the dim faded remnants of the first generations of stars. Together, these cosmic cemeteries hold the slow stellar history of our galaxy. Globular clusters are particularly rich in old stellar remnants. Each globular cluster is a tightly bound spherical group of hundreds of thousands of stars formed in the early universe and largely undisturbed since. Old white dwarfs and neutron stars accumulate in the central regions of globular clusters over billions of years, producing some of the most ancient stellar populations known. M4, also known as NGC 6121, is the closest globular cluster to Earth. It lies about 7,200 light-years away in the constellation Scorpius. Hubble Space Telescope observations have identified some of the oldest white dwarfs in the universe within M4, with cooling ages of more than 13 billion years. These are among the very oldest stellar remnants ever observed. 47 Tucanae is another famous globular cluster in the southern sky. It contains millions of stars in an extraordinarily dense cosmic configuration. Within its core, neutron stars and millisecond pulsars from the early universe still rotate and pulse. Some of these neutron stars have been continuously evolving for more than 10 billion years, slowly cooling and slowly winding down their stellar rotation. In the inner regions of dense globular clusters, stellar interactions are common. Two neutron stars can sometimes pair into binary systems through gravitational scattering. White dwarfs can be exchanged between binary partners. Sometimes, two stars actually collide and merge. These slow stellar interactions taking place across cosmic time produce a diverse population of stellar remnants and unusual binaries. Beyond the globular clusters, the broader galactic halo contains many isolated stellar remnants. The first stars in the universe, sometimes called population 3 stars, were extremely massive and short-lived. They probably exploded as supernovae and hypernovae more than 13 billion years ago. The remnants left behind, mostly black holes, may still drift through the galactic halo today, far from any present-day stellar activity. Iron stars, in the theoretical sense, are predicted to slowly form across spans of cosmic time far longer than the present age of the universe. After unimaginable stretches of cosmic time, the slow processes of quantum tunneling will gradually convert all matter in old white dwarfs into iron, the most stable element. The resulting iron stars would be solid spheres of nearly pure iron, drifting in the deep cosmic dark. They would represent a final stable state of stellar matter, held in place across timescales beyond all imagination. Black dwarfs are another predicted final state of stellar evolution. After a white dwarf has cooled completely, no longer emitting any visible light, it becomes a black dwarf, a dim, solid stellar remnant indistinguishable from the surrounding cosmic dark. The cooling time required to reach the black dwarf phase is far longer than the current age of the universe, so no black dwarfs exist anywhere yet. They are objects of the cosmic far future. Neutron stars also slowly cool and slowly spin down across cosmic time. Eventually, the active pulsar phase ends, and the neutron star becomes a quiet, rotating remnant. Over much longer timescales, the rotation slows further, the magnetic field weakens. In the very far future of the cosmos, the remaining neutron stars may simply drift through the galactic halo, spinning quietly with no detectable signal. Black holes from massive star deaths slowly accumulate as well. Each black hole keeps the mass it received at formation, plus any matter it has accreted since. Some black holes are completely isolated, having lost their original surrounding stellar material. Others remain in binary systems with surviving companions. The total number of stellar mass black holes in our galaxy is estimated at 100 million or more, though only a small fraction have been individually identified. In the very far cosmic future, the slow cooling of all stellar remnants will continue. The universe will expand. Galaxies will drift further apart. star formation will slow and eventually stop, as the available cosmic gas is locked up in remnants. The cosmos will gradually transition from an era of active stellar life to an era dominated by the slow cooling of stellar remnants and the patient drift of cosmic darkness. Even further into the cosmic future, the predictions of theoretical physics suggest that the proton itself may not be perfectly stable over timescales of perhaps 10 to the 34th power years or longer. Some theories predict that protons will slowly decay, gradually disintegrating into lighter particles. If true, then all matter, including the slow black dwarfs and iron stars of the deep future, will eventually disperse into a thin cosmic mist of fundamental particles. Black holes themselves may also slowly evaporate, according to predictions by Stephen Hawking. The Hawking radiation process slowly removes mass from black holes through quantum effects at the event horizon. The timescales are extraordinarily long. A stellar mass black hole would take 10 to the 67th power years to fully evaporate. But across enough cosmic time, even black holes may eventually disappear, leaving only a faint wash of radiation in the surrounding cosmic environment. Tonight, the cosmic cemeteries throughout our galaxy continue their slow accumulation. Every supernova, every nova, every white dwarf cooling adds something to the long history. The remnants are the patient archives of cosmic chemistry, carrying the elemental signatures of every stellar life that has come before. They are the foundation upon which future stars and planets will eventually form slowly across cosmic time. The same processes are happening in countless galaxies across the universe. Each galaxy has its own globular clusters, its own halo of ancient remnants, its own population of stellar mass black holes. Together, the stellar cemeteries of all the galaxies in the cosmos hold the patient long history of all stars that have ever existed in the observable universe. Tonight has been a quiet journey through some of the most unusual stars in the cosmos. We have visited the small, dense neutron stars, the precise pulsars, the magnetars with their extreme fields, the Wolf-Rayet stars in their late mass loss phase, the enormous hypergiants, the cool red supergiants, the small failed brown dwarfs, the cooling white dwarfs, the pulsing Cepheids, the orbital binary systems, the rare black widow pulsars, the volatile Carinae, the most energetic Hypernovae, the chemically unusual carbon and helium stars, the theoretical exotic stars, and the slow accumulating cosmic cemeteries. Each one is a quiet part of the long story of stellar life and death across the cosmos. Now we will gently begin to bring tonight's journey to a close. The rare stars will continue their slow, patient existence, whether we are watching or not. The universe will continue to evolve, and we will return gently toward the rest we have been carrying with us all along. Thank you for letting us be part of your night. If this slow journey helped your body settle, subscribing is the kindest way to keep these hours coming. Each week, we travel somewhere new and ancient and unhurried, always within the cosmic world of the rarest stars in the universe, always meant for rest. Good night. Sleep deeply. Sleep slowly. The neutron stars are still spinning quietly in their distant orbits tonight, releasing their faint cosmic pulses across deep space. The Magnetars are still humming with fields 1,000 trillion times stronger than anything ever made by human hands. The Hypergiants are still slowly shedding their outer layers into patient nebulae of gentle cosmic dust, exactly as they have for ages. They have been here long before you, and they will be here long after. And tonight they keep you company while you rest. Good night from the Circadian Institute. And with that, we bring tonight's quiet journey through the rarest stars in the universe to a soft close. The neutron stars are still spinning, the magnetars are still humming, the hypergiants are still slowly releasing their gentle outflows. They will all continue without us. Sleep softly tonight.